Okay, folks, I think we're live. Just wanted to say before we start, we're reviewing this paper, Learning Sparse Neural Networks through L0 Regularization. This is sort of part of our current research focus of seeing how we can apply sparsity to deep networks, biologically inspired sparsity. The way we see it, how does the brain use sparsity? We know that it's super important. We think that it's critical for intelligence as a sparse representation. So we're looking at machine learning papers that have to do with sparsity. One sec. Okay, no problem. Coordinating with Marcus on the Numenta end. I'm in Watsonville right now. So thanks for watching. We'll start in just a few moments, and we're going to go over sparsity and neural networks. Learning sparse neural networks through L0 regularization. We're just working out what's getting shared. So I'm going to turn off my screen share for just a moment, and we'll cycle through these two cameras in my office. Are you guys ready? You want to turn the on-air sign on? Okay. It's all right.
Okay. I think we're ready.
You guys let me know if audio is good, please.
Sure, I'm recording on our side too. I'm guessing that's a yes, Matt. Cool, I can start then. Cool. Okay, and we're good. So I've been looking at this this paper, Learning Sparse Neural Networks through L0 Regularization, from Louisos and Welling and Kingma. A couple of these people are the ones who created variational autoencoders. But that's sort of an aside that has some overlap with this, but you don't need to know about those to understand this. So the title says L0 regularization, but I'm not going to talk about it in those mathematical terms. I'm just going to say they count how many synapses there are, or they count how many non-zero weights there are. And it's like they reward networks for having non-zero weights. So their overall goal is neural networks where most of the weights are exactly zero. So sparse networks by kind of that definition of sparsity. And the motivation is, I would say, it's primarily computational efficiency. Also to prevent overfitting. They found that it can be good for that as well. But I feel like a little more of the focus here is on computational efficiency. And the idea being that the fewer of your weight, the more of your weights that are zero, the fewer operations you have to perform on each.
So just to be clear, they're not talking about sparsity of activations.
Correct.
Just sparsity.
Correct. Just the connectivity. So it's like in one, input comes into the network, input feeds up through the network. How many floating point operations just happened? Yeah. They're lowering that number. And so that's the general idea. And I'm going to jump a little bit ahead to talk about what their solution looks like. And then I'll take a step back and explain how they got there. And by the way, this presentation is focused on laying out, describing it, so we can kind of evaluate it on those terms. I'm not going to put it into context of other methods for sparsification. I want to study some more before I tell how well this method performs relative to others. I'm not ready to talk about that, but their model itself is, I think it's elegant and nice and worth looking at. So, but I plan on doing a little more with this, understanding how it fits in the broader context after this. So, if I were to just like over compress this and just simplify it to just say like broadly what they do something a little bit like having permanences on connections, except the permanences are probabilistic. So you can imagine like we have something called a permanence where we evaluate how connected two cells are. If it's above a threshold, they're connected. Theirs is a little different. It's like rather than being above a threshold, it's like if permanence is 0.5, half the time it will be connected, half the time it won't be. And just to be clear, that they never use the word permanence. That's just the word I'm overlaying on this. So to say that more formally now, each of the weights in each time step is it has a stochastic element to it. So there is the actual learned weight. They denote it as technically the paper uses theta because they wanted to talk about parameters in general, but I just switched to using W because I just want to talk about weights. The learned weights are, as they always are in neural networks, they're not. Sometimes we talk about getting rid of weights. That's totally orthogonal to this. That's not what the goal here is. So they have learned weights as any network, but they have this extra factor between 0 and 1. I should have written it. Well, I draw it here. This extra factor between 0 and 1 that acts as sort of a gate. And this factor, this Z, I've drawn just a picture of the type of probability distribution they use, where with some probability, Z is going to be exactly 0. The weight is going to be just completely 0. With some probability, it's going to be exactly 1. And they do have this possibility that it's somewhere in between as well.
You've shown that as being less likely. Is it biased towards 1 and 0?
Yeah.
With a small, so it's not a simple probability. It's got this sort of bathtub shape to it.
So right. I would say it's a mixture of discrete and continuous. So I would say, like, just to make up some realistic numbers, there might be like a 40% chance of being 0, a 10% chance of being 1, and then the remaining 50% is kind of distributed through this. And just to finish this little part, the nice thing is, and this seemed a little magical to me. I wasn't sure how they pulled this off. I'll talk about it later. They train these distributions such that like if having this connection is not advantageous, the distribution over time will shift this direction such that it most often is 0, and it will, if it is advantageous, the distribution will shift in this direction. So they're actually modeling, their network is taking advantage of the idea that a synapse is stochastic, that a synapse sometimes doesn't work, sometimes does. It sometimes might have more effect, sometimes might have less. And they're actually incorporating that into how all of this works.
This is interesting because I think this is closer to perhaps biology than what we do. And we said, okay, let's just go to binary and put a threshold on it, right? But this is probably closer to what is actually happening.
That was my impression.
But it's not clear what the advantage of doing this is. It seems the advantage is getting to these end states where you really, either the synapse is important or the synapse is not important.
Yeah.
And the in-between states are, in my mind, I don't know where you're going to go with this in this paper, so I can't speak for the paper, but in my mind, it's like, okay, those in-between states are, just a fact that the biology is like that. It's growing these little synapses, and in the beginning, there's this little Philopedia. They don't really work very well. Mm-hmm. So, and so it's not clear what I'm going to gain from doing that. Maybe you're going to tell us, maybe there's something, maybe they don't. But it's interesting to say this is probably closer to biology. We just skipped to the end game there.
Yeah, yeah. I feel like it's a step in the right direction. It's a step toward biology. They still have these weights and everything, but it's a step in the right direction.
Yeah.
So is the W tilde dense?
Yes.
So that's always going to be dense.
Yes, it is, but it's kind of non-meaningful. But for any of these z's that are largely in the zero, it's almost like a weight is there, it's orphaned, it's kind of a hack, it's there, but it's not
Well, it's
actually.
interesting
But there's a computational cost. You're still gonna have computation.
Unless it's zeroed. I'm sure, zeroing it has a cost, but.
Interesting, this is another slight difference in what we do. We assume that in biology, you can't have a dense matrix like that. So we just assume there's a subsampling potential synapses, which is sort of like gets you closer to the end games in the beginning. Like we just don't even assume you can form all these synapses, you know. So I'm only saying this to contrast it, just to see how it's compared to what we did. It's interesting.
And is it, so even at inference time, they do this probability?
Yeah. And now in principle, they could, for inference, they could just sample a random set of Z's. They could just sample a mask once, just sample it, and just use that forever for inference. There's no advantage. It's not like inference consists of doing multiple passes. So they could just sample it if they want. They kind of leave that open.
It seems like if you wanted to get that computational efficiency, you kind of want to do that.
But yeah, that's real.
I think that's your dense comment, right? Your dense comment. So if you have a dense W, what's the point of you have to do everything?
And yeah, they could even, they don't necessarily have to sample this, they could choose just a set of zeros and ones. Then anyway, they have options like.
So I'm assuming that this in between states are going to somehow come into play during training.
I'll talk about, because these next two steps, I'm going to first talk about why they use probabilities at all, like why they have the 0 and 1. The second part, I'm going to talk about why they have the in-between state.
Okay.
So those are kind of two separate questions. Yeah.
When they train, do they also train in between state? Do you train the whole distribution, or is it just training the 0 and 1 probabilities?
So they have a single parameter that causes this curve to shift, and it causes like the curve will it'll move. Like technically, the term they use is alpha. I haven't labeled it a permanence here, but a single parameter causes this whole curve to shift, causes all the mass to move either from here over to here. It's just a single parameter, a single number.
What is this beta doing? It causes temperature?
Yeah,
How it changes it?
yeah. So
beta.
and I haven't drawn it on the board, but their formula. Okay, so I've drawn just a cartoon. I've drawn just a curve here. An equation underlies this curve, and that equation has a couple parameters: alpha and beta, which they hold constant. Betas, they call it a temperature that kind of causes the curve.
It's a constant.
Yeah,
Hyperparameter.
yeah, they set it constant to 2/3. They didn't train it. They could have trained it, but they chose not to. So yeah, it's just the beta. You can just think of it as a constant that causes the curve to have this shape. So yeah, I can move on to okay, what caused them to land on this solution? I'm going to do it in two parts. First, why probabilistic at all? Why make Z stochastic? Z here is, I drew a little vector sign above it. That means it's a mask. So like Z, this was an individual weight. The Z vector is like, why is the connection matrix a random variable? Or the connection vector. So the reason for this is, stepping back to like the original purpose of this, they want the network to, since they're training these networks, they want a cost function that gives a big like reward or big negative cost to having a weight that is truly zero. Having a connection that is zero, not low.
Cost to that? Isn't that a desirability?
Yeah, so I said negative cost.
Oh, I think I missed that. Okay.
So yeah, the point is it wants to reward
You want to get more
non-zeros
zeros.
or punish non-zeros.
Yeah.
So I'll describe it that way since we're saying cost. We want to punish non-zeros, and that inherently has like the thing here is they specifically don't want to punish 1.0 more than 0.5. It's just like this is like a discrete reward. If you're zero, here's your reward. If you're not zero, you don't get this reward. that inherently is a very non-smooth reward function, a very smooth, a very discrete cosine function. And this whole approach of using infinitesimal gradients to figure out the best network just doesn't work when you're using those types of functions. So their general way to solve that is if you make this mask, if you make the connectivity a random variable that looks, that just looks something like this. Let's just talk about like a Bernoulli random variable, just discrete. It's either 0 or 1 with some probability pi. It's 1, otherwise it's 0. If you use this distribution for the mask, which would be just like almost like a permanence is probabilistic in the most literal form. If you do this, that solves the problem. That makes it where now you can make your cost function. What is the expected cost, the average cost, the average error, you could call that. What is the average error of this network under these probabilities? Now, if you change the probability on a specific synapse, just take one synapse, change its probability just slightly, this cost will vary smoothly because you're moving the probabilities a little bit. You're going to cause everything to change. An infinitesimal change here is going to cause an infinitesimal change there. By this pair, these two steps of choose Z randomly and use the expected value, weighting in the probabilities of everything, that gives you a smooth cost function. Problem is that this is not tractable to compute. A summation over all possible masks, that means you have 1,000 cells, that's 2 to the 1,000, summation of 2 to the 1,000 elements. So the next step they had to do is they need to not compute this directly, but approximate it by.
I didn't understand why this is tractable.
Yeah.
I mean, your Z function there is just it's just a set of probabilities, right? So you're just doing this expected cost based on probabilities out there.
Right.
Why is it? I'm missing what.
So just the formula would it's in principle solvable. It's in principle very simple, but I mean what I've drawn here is actually going to be like if I were to expand this out, I would be like, okay, P of all zeros times the cost of all zeros.
Mm-hmm.
P of 999 zeros and 1.
But you have to do that.
You would have to expand this out.
You're summing over all Z's.
Oh yeah, over all possible Z's.
Interesting. I thought if you're training the system, you just pick whatever the currency is and then train on that. I guess I'm not following.
Okay.
But I was just surprised.
You're right that I haven't.
The Z is going to change on every iteration.
Yeah, but you don't. Why do you have to? You could just train on this training pass. This is my Z.
Okay,
right?
so it's funny. Like you're pretty much saying what they end up doing, but okay. The thing that's being trained is these underlying parameters, and you pretty much are saying what they do. I almost think I should move on and just go on to what they actually do.
Okay.
So.
All right, I understand. You answered my question.
Yeah.
If I have to do this calculation over all possible Z's, then it's impossible.
Yeah. So because in any particular time steps, what you have is the set of probabilities, the set of these. What is every sells one of these? Every combination is still possible. Every possible vector is still possible.
Is this a wave function, or am I collapsing to some point? I'm assuming we just collapse at some point and calculate that one. But if you want to calculate all possibilities,
you're pretty much getting it. That's what they do. Well, I'm going to move on. So rather than expand this outward, you can approximate this by just sampling a few of these, sampling a few Z's. Not just choosing Z's randomly, sampling them from like what are some likely masks? Taking a few likely masks and just averaging across those. This is the notation that's often used when you're sampling something. Put in like parentheses. parentheses above it. Take a few samples of it and averaging across them. And they go a step further. I didn't write this here, but it's exactly what you said. They only sample one of these.
Yeah, because you're going to do this over and over and over and over again. So who cares if you just one time you got the wrong?
Yeah, that's and they came to the same conclusion, which is appealing from a biological sense. That during learning, whatever happened, it'll just learn.
Yeah, whatever happened. This synapse released some neurotransmitter, right?
Yeah, and they found that doing a bunch of samples didn't have much benefit.
I wasn't thinking from a biological point of view. I just felt like you would end up getting the same result anyway. If you're just doing one of these calculations, well, then you might get it wrong. But you have to do this a million times or something, so it'll average out over time anyway.
Yeah. So okay, that is their approach. They are sampling a random mask in each time step. Your problem is now that if your z's looked like this, and you want to train these pies, you want to figure out, do you want them to be larger or smaller? You're back to a discrete cost. As you change these, say you choose a random mask, and then you decide, okay, how do I want to change my probabilities? Changing a probability will either have no effect, or it'll have this big stepwise effect as it causes cells' weights to just change. The point is the cost function is no longer smooth because we've gotten away from doing expected cost. It's no longer smooth. Everything's going to be discrete. Either has no effect or this big stepwise effect.
So I think that might be a problem for the training methods.
Yes, and that was where they make it now that as you vary pi, as you vary this parameter that's controlling what z is going to pop out, is that if they have this in between continuous zone that is like between these two discrete points, then that changes it so that changing pi either has no effect or it has a smooth effect. Either has no effect or it has a continuous effect. So mathematically, this solves this problem. This makes it where everything can be approached as gradients. Everything can be approached as changing things infinitesimally and getting an infinitesimal change, a slope. So that was where they took advantage of this. That's where they needed this. They needed this in between continuous zone because this can't be computed directly.
So the question is, I mean, we really want a discrete function, and we really want to promote zeros disproportionately.
Yeah.
And otherwise want it to be 1.
Yeah.
Right? So and optimization techniques can't handle that. So they go through all of this.
Yes.
But at the end of the day, have we lost that property? Is it still really encouraging true sparsity?
Yeah.
Or is it going to get stuck in one of these in-between zones?
So I'm glad.
You're just saying, are you asking whether this will actually get you to your end goal?
Yeah, because now you do all of these steps to get away from the discrete thing, which is what you really want.
Yeah. So you've lost the ability to.
I guess that's just a question. And maybe
I guess if a weight goes to 0, then all of a sudden you have this big reward, right?
That's what we want.
Yeah. So I can answer that in 2 ways. One of those answers is going to be I should experiment with it directly and see what these end up looking like as I train it and see what they are. They may have answered that. I don't think they did though. A slightly more satisfying answer is in this world of probabilities, what they're rewarding the network for is how much of its mass, how much of the probability mass is here. Anything, or I should say, it's punished for how much of its mass is over here. How much of its mass is, if any probability mass is right here, it's bearing cost for that. It has no cost for any mass that's here. So there is a strong incentive for this to be exactly 0, because any mass that's right here is paying the same cost as any mass that's over here. So I would say that like the vast majority of the mass in this network is on 0. Now, does a lot of it lie in this in-between region as opposed to on 1? I don't know. So that I can't say.
Did they give any numbers in the paper on this? I mean, did they talk about how well they actually achieve sparsity?
They plot it against other techniques. They show that like the number of parameters, the number of effective parameters is shrinking constantly over time, and they compare it to other techniques. But that's the best I can say. I can't right now. I can't tell you like they achieved 5% sparsity. I'm just making that number up. So that's more getting into the results where I'm still getting a good picture in my head. One thing I'll kind of mention, I don't know. If it is landing on these in-between values, that's not really going to serve a functional role. It's not going to like act as a weight because it's just so random. It wouldn't be a very good weight. Nobody raised that.
Because during inference, you're still applying the probability.
Yeah. So
they're kind of like, just kind of like floating around, not noise functions.
Yeah.
But if you're one, if your weight is one, wouldn't you still be applying that probability? The weight is 0, and then I do inference. Is there still a probability that it might not be 0? Like, or is it get to the lower picture where it's really 0 and there's really almost nothing else, and it's really 1. It's really, you know what I'm saying?
I'm sorry, I'm not asking questions.
I'm not just getting confused. But,
yeah, maybe the last thing I was pointing out, when I looked at this, I was a little worried that these in-between values would just be, if the network would somehow be storing weights here, like a hacky version of weights. And I don't think it's going to do that. That's all I was saying, because it's so unreliable. It's always hopping around.
Maybe that the way they chose this data, maybe the data controls this in some ways. It's really forced down it's barely continuous in some sense.
Oh, because beta is just the probability that it's in your bucket there, and it might be pretty low.
It kind of widens the distribution. It makes it more. Beta is temperature. They call it temperature, so it's like it widens it. So okay, final part I'll talk about. So I said early on that this was kind of magical to me, that you could train a probability distribution. And I'm phrasing it in ways to make it appear magical. There's a straightforward way to do this, but it's once you know the straightforward way, it's obvious. But I didn't know how to do it, and it's elegant and it's used elsewhere. It's not just in this model. They call it in other papers they call it the reparameterization trick. It's this trick that you'll even see titles of papers and talking about the reparameterization trick, and it's clever. So like here's like the question of how I've drawn this and kind of the sometimes when people depict back propagation, they'll draw like a gradient passing back through this network. You then you use this to figure out how to change the weight. You use it to figure out how to change this. It was like black magic to me. How would you take a gradient and update this curve? What does that even mean? And the answer to this is if you can generate random numbers, if you can sample this distribution, however it is you're implementing that, if you can pose it as okay, first just generate a random number between 0 and 1, just anything. And by the way, it's just kind of a coincidence that I'm using 0 and 1 here and also using them here. Like this could have been generating random between like 47 and 49. This could have been anything. But if you have a random number generator that just does the simplest thing in the world, it just generates a floating point number between 0 and 1. If you can start with that and then do a bunch of math to get your final result, it still is the case that backpropagation, when it arrives at the random step, can't do anything. But because you've set it up in this way, gradient comes back, comes here, it can now update your parameters. It can now update the parameters that you used to take this simple distribution and convert it into your advanced one. And this way of posing the problem is really nice. And it just makes it where, of course, you can train this via back propagation. And so that's how you take a random distribution and train it, is by, I'd say, pushing the randomness further back and then training the in-between steps.
I didn't follow that, but I don't need you to explain it again, because I don't think it's that important. You're explaining a detail of the system, right?
Yeah.
That it's an
But
implementation.
it's something that's going to come up in a lot of, it's a good strategy that's worth knowing about. So it's not necessarily.
I didn't quite understand. You just said, okay, I have to update this distribution. Now I'm going to start with a random distribution. Now I can do it. I don't know how that works.
For those of us who are like just setting up these networks, it's cool to know this trick. For you, just know that it's possible to train the distribution. Okay.
It's possible.
Okay. The goal here is you want to be able to update the probability
Yeah,
distribution.
got it.
And the trick here is
So if I can understand what you said, is
Yeah.
you want to rewrite the probability distribution so it's a function of a uniformly generated random number and some other parameters. And if you can do that, you can just
Why
optimize those.
is it easier to update a random number than a distribution?
You don't update the random number.
Oh, I see.
That's like a constant.
I see. You're combining something like what you're labeling alpha permanence here with this random number.
Yeah.
And now I can update the one and just assume the random number is random.
Yeah.
Okay, got
Yeah.
it. Okay.
For me, this was a big aha moment as I read this, so it's worth sharing at least for some people. So anyway, this is how their model kind of works. In the end, I think it's pretty simple. I mean, it's has these what I'm calling kind of probabilistic or stochastic synapses, and making where most of the time, most of those synapses are going to have weight 0. Sometimes they won't, and that's how it sort of explores: should I form a connection here? Should I get rid of a connection, et cetera. And this strategy feels like it's just kind of a natural result. If you think about the problem for long enough, how you're going to train sparse networks, it feels like this is where you're going to arrive. It feels like a logical conclusion, of almost like they discovered this rather than invented it. So it feels nice. I like it.
Train sparse backprop network.
Yeah, sure. No, good point. Good point.
We train neural networks without doing this. If something. Is it fair to say, we're going to take a bunch of sort of, starting with a bunch of convolutional neural networks, fully connected networks, and the backprop training. And now we want to make sparsity, maybe sparse connections. And there's multiple methods for doing this. One way is we're exploring other methods now, right? Where you could sort of randomly make some things 0 and see what happens, or there's different methods for going about this.
Yeah.
And this is another method. Would that be a correct assessment?
Yeah, I think so. One thing that they kind of pitched about this method that makes it an especially nice one is a lot of those methods involve training dense and then like creating it into something else.
Yeah.
Whereas this is like during learning, it's just continuously kind of getting rid of its parameters essentially.
Yeah, so maybe more efficient than because you don't have to train the dense network.
Yeah, or like starts out somewhat dense.
Yeah.
It also has this nice, like it starts out like kind of probabilistic sparse. It kind of starts out like a lot of these are going to be kind of on, kind of off, maybe mostly off. And then the ones that are useful will kind of come on.
It seems to me that, and this is just an intuition as opposed to more than that if you actually had sparse activity, then your whole way of thinking about this to begin with might be different. This is assuming you don't have sparse activity and you're trying to figure out how to get sparse connectivity. But if I started with sparse activity as an assumption built into the network, then I might come up with a whole different set of methods for going about this. Is that just strikes me as maybe true? Is that
It strikes me as maybe true. I can't refute that or really support it either.
So
I don't know, maybe.
it just feels like that.
It's
I mean,
worth
you can still
considering.
use this technique with sparse activity.
Yeah, but I'm
It'll
saying if I have
still work.
sparse activity, then I'm trying to imagine where, the end game where I think, okay, how do brains do this? Well, they got sparse activity and sparse activity, a whole bunch of other stuff going on. And they don't do back prop in this sense at all. But I mean, in some sense, you're trying to take a system that's designed for full connectivity, the existing deep learning networks, and you're trying to figure out how to introduce some sparsity at one point. And so you have to go through a little bit of hoops to do that. Because the system doesn't want to do that. Like you said, maybe people start out by fully training a network and then figure out which ones to get rid of later, or this is the way of making it a little bit more efficient. You can sort of make it from the get-go, have some things that are, but it's still acting as if it's fully from the get-go, have some sort of pseudo sparse. Whereas if you just said, hey, I've got sparse connectivity and sparse activity, and the sparse activity forces, it's a very different type of network when you have sparse activity. It's a totally different way of representing information. You don't have all the subsets I talked about. You don't have these overlap problems and so on. It just seems like you might end up with a different set of solutions if you started with that as your assumption. It's just a gut feeling that that's the case.
I'd also point out there is a newer paper, the one I sent you, it's zero sparsity, and they tried to reproduce several sparsification methods, this one included, and they could reproduce all of the methods except this one. So this one, they couldn't scale to larger tests like ImageNet or translation problems, for example, from English to German. They couldn't make it.
What happened when they tried?
Yeah, they tried like several different approaches, several different hyperparameters.
Or just didn't work well?
It never converged. So that's
Just like harder, like for this they did SciFar, it was the hardest thing they did.
Yeah, the hardest thing they did SciFar. So they said they emailed the authors as well. So I think there's some ongoing discussion if this method would scale, like more complex.
Interesting. Was there any intuition why it might not scale?
So they said they don't have. They're just they emailed the author. They're having discussions. They said they found like a small error maybe in the code or something. But they didn't provide like any intuition.
So that's an open.
It's an open question.
Yeah. Interesting. Yeah, I would say my motivation for presenting this was that it's theoretically appealing. I did not present it because it's amazing results. Maybe the results are good. That's not what motivated me.
It's a nice, different way of seeing sparsification.
Yeah.
Yeah, it'd be really nice to know, even in the one they tried, how sparse they got. Just looking at their charts, it's a little hard to tell. They're comparing flops.
Yeah.
And they don't really give the factor, and you can kind of guess, maybe it's like a third, or no, not a third, maybe a quarter or a fifth of the, maybe end up with 10 to 20% non-zeros, roughly in that range.
Yeah.
It's really
So it's sort of like they're trying to take a fully connected system and come up with some way of breaking the symmetry of it. It's like, going to binary, so like breaking the essence of a fully connected network, or really these back propagation networks. So it feels like they're trying to say, okay, we want to be sort of like a fully connected network of all these high precision weights, but we really don't want to end there. So how do we break that symmetry of that system? Where if you started with a system where you have your connectivity matrix is inherently sparse to begin with, because it's like a potential synapse pool.
Okay.
And in that potential synapse pool, your synapse into a 1 or 0 or something like that. Then you've already broken the symmetry of the system to begin with. It's like, everything can't be connected to everything. It's just never going to happen. You're going to be sparse one way or the other. So now all you're doing is optimizing within some sparse connectivity how to make it even sparser. That's how a few brains would be doing it. And so it's a sort of different problem inherently when you start with a sparse pool, like not every synapse, every neuron connected. But I'm just trying to think about the problem very holistically. What's going on here. I'm thinking out loud. So that was interesting.
I think it'd be interesting to see the histogram of the Z's during various times of training to see how that distribution edges out toward the zeros and ones, because that answers kind of what you're gaining as far as the sparsity goes. the worry that you mentioned of having a lot of coefficients near 0 and near 1, but not actually getting to 0 and 1, I think is valid, and it's a question of whether this thing forces things to take the leap over and actually get rid of a connection.
Yeah, I feel like getting rid of the connection is going to happen a lot, but just because that's exactly what the cost function is rewarding, or what is punishing is punishing non-zeros. But
Yeah, and the graphs kind of show that as well. It,
Yeah.
it definitely does happen. It's just what are the percentages? What are the actual
Right,
numbers?
I think you can tell the sparsity from this other paper. Look at the state of sparsity. They show the sparsity graphs and then compare methods so you can see from there.
Okay,
yeah, I'm planning on reading that.
cool. Thanks.
Thanks, good.
Cool. I think that's it for
Thanks, Marcus.
the meeting.
Yeah.
Okay, I'm going to shut off the live stream now. So thanks everybody for watching.